This video is on electrophilic addition. And our aims for this video are to be able to know what a carbocation is, and to understand the relative stabilities of primary, secondary and tertiary carbocations, and also know what is meant by primary, secondary and tertiary carbocations, to be able to draw the mechanisms for the electrophilic addition of hydrogen bromide, sulfuric acid and bromine to any given alkene, and understand why bromine can be used as an electrophile, because you'll understand as we get further through the video that an electrophile must have certain properties, and bromine doesn't seem to have those to begin with, and so we're going to understand why bromine can be used as an electrophile despite this. So first we need to understand what a carbocation is, and what a carbocation is basically an alkane that has lost a hydrogen somewhere. So you can write a general alkane as being a C with 3 groups or 4 groups around it. One of them being at least one of them being hydrogen, and the other 3 could be hydrogens or carbons attached to them. We're going to call them R groups for now. And when a carbocation is formed, basically this hydrogen here is not there anymore, and so we're just going to delete that. And so when that hydrogen is lost, or in fact in electrophilic addition it's a bromide ion that's lost, but that bond is not there anymore, and what is formed is a carbocation which has a positive charge like that. Now this carbocation will have different stabilities depending on what these 3 R groups are. Because obviously this carbon does not really want to be positively charged, but if it can be supported in some way via electrons being pushed onto it, then it'll become more stable. And so the more stable this carbocation is, the more likely it is to form. So let's think about how this carbocation could become more stable. So those 3 R groups could be either alkyl groups, or they could be hydrogens. So a primary carbocation is a carbocation that has 2 hydrogen groups and 1 R group. So that is called a primary carbocation. You could then have a positively charged carbon that has 2 R groups on it, and also 1 hydrogen left over. That would be called a secondary carbocation. And then finally you could have all 3 of the groups around the carbon, all of them being R groups, and that would be a tertiary carbocation. Now these 3 types of carbocation are have different stabilities, and the stability arises from the fact that these R groups, if they are carbons, which they are in these cases, if these are carbons, so either methyl groups or ethyl groups, then those methyl and ethyl groups have more electrons than a hydrogen does by itself, and so those electrons can be pulled towards the carbon via this covalent bond. And so the more R groups there are around the carbon, then the more stable this carbocation will become, because these these R groups will give what is called a positive inductive effect. So the more R groups that are giving this positive inductive effect, and the positive inductive effect is the idea that electrons are being pulled through that covalent bond towards the carbocation. So this is known as a positive inductive effect. The more directions that can occur in, then the more stable your carbocation will become. So a primary carbocation is less stable than a secondary carbocation, and a secondary carbocation is less stable than a tertiary carbocation. And this has an effect on electrophilic addition mechanism, because often there'll be a choice in which the positive charge can form on 2 different carbons, and the carbon that is more stable and therefore has more R groups around it will be the one where the positive charge forms, and I'll show you that when I show you the mechanism a bit later. But the take-home message from this slide is that the more R groups, the more alkyl groups, i.e. the more carbons that are attached to the positively charged carbon, the more stable this positive charge will be. So let's look at the mechanism for electrophilic addition. We're going to do that between hydrogen bromide And electrophilic addition occurs between an alkene and an electrophile, such as hydrogen bromide. Now we're going to use this alkene here, which is propene, and you can see that there is a methyl group attached to one carbon, but only hydrogens are attached to the other carbon, and that's going to be important later on. And that is reacting with hydrogen bromide, and we're going to draw hydrogen bromide in the following conformation, like this, with a hydrogen above the bromine, underneath the double bond. The reason we do that is because the reason why hydrogen bromide reacts with this alkene is because, firstly, there is a dipole in this molecule. The bromine pulls electrons away from the hydrogen through the covalent bond because it is more electronegative. And so we can say the bromine is delta negative and the hydrogen is delta positive. This delta positive hydrogen is attracted to this area of high electron density, this double bond, and so it reacts with it. So the first step in this mechanism is that this double bond will reach out and attack this positively charged, or this slightly positively charged hydrogen, and we can show that using an arrow that goes from where the electrons are to where the electrons are going. Now in doing that, that will force this bond here to break, and the electrons from this bond will go onto the bromine. So what will be made is a carbocation so we've got H on this side, H and CH3 on this side, and we're going to decide which side the hydrogen will go in a second, and we'll also create Br minus. Now the hydrogen that has been attacked by this double bond has a choice of where to go. It can either go on this carbon or it can go on this carbon, and the side that it decides to go is influenced by how stable the carbocation it will make will be. So either a positive charge could go on this carbon or it could go on this carbon. We've got to think about which one will be more stable. This carbon only has two hydrogens attached to it, whereas this carbon has a hydrogen and the methyl group. So this carbon will be more stable as a carbocation, and so the hydrogen will attach onto the carbon with the most hydrogens attached to it, which is this left-hand carbon here. The final step of this mechanism is this bromine reacting with this positively charged carbon and adding to it, and then the final product is the following. Notice that when I drew the arrow from the bromide ion, it came from a double bond. You must make sure you add, sorry, not a double bond, from a lone pair. So you must make sure you add a lone pair to the bromide ion for the arrow to come from. Arrows should always come from either a lone pair or a bond, like it has done in this first case. So what I'm going to do now is just show you a quick animation that I made that will hopefully bring this mechanism to life slightly and show you in a bit more detail, a bit more visually what is actually happening when the bonds break and when the lone pairs attack different parts of the molecule and things like that. So I'm going to talk you through it. I might have to play it a couple of times so you can look at different parts different times. So the first thing that happens is that a dipole is already formed on this slightly positive hydrogen, slightly negative bromine. And the reason why this double bond attacks this hydrogen is because of the dipole. You can see the double bond attacks the hydrogen and this bond will break, form bromine. Now the next step will show you what happens. So you can see up here that the hydrogen, so if I just rewind that slightly, go back to the arrows. What I want you to do now is just focus on this top bit. Don't worry about what the bromine's doing for now. I just want you to look at this bit here. So you can see that when this bond breaks, the bond breaks and forms with the hydrogen. Now this hydrogen has an option on which way to go, and it goes to the left-hand side because this carbon, or this carbocation, will be more stable because it has a methyl group attached to it. Then what will happen is that the negatively charged bromine will attack this positively charged carbon, and eventually a bond will form between them. The lone pair will form a bond with the carbon, and then the charges disappear. Now if I just take that back slightly, to where the hydrogen bromide broke. What I'd like to do now is just focus on this bit here. Okay? So this bond breaks. The pair of electrons, from that bond is now on this bromine. Now, one of these electrons was with the hydrogen originally. The other electron was owned by the bromine originally. Remember, they share an electron from each atom. And so this bromine now has, or this bromide ion, now has an extra electron that it didn't have before. And that's why it's negatively charged. If you just keep on playing, this doesn't harm you to watch it again. So the hydrogen migrates to the side where it makes a more stable carbocation, and then this negatively charged bromine is attracted towards the positively charged carbon. It's the lone pair that attacks the carbon. Remember, the arrow will come from a lone pair or from a bond, and then the lone pair will form the bond with the carbon. I'm now going to show you the reaction between sulfuric acid and an alkene. Again, electrophilic addition. We'll choose a different sort of alkene to do this with, so we'll have CH3s on this side, and a CH3, and an H on this side. The reason I'm showing you all of these is because sulfuric acid is quite difficult to draw with all the bonds. So this is the way you draw it. You've got sulfur, double bonded to two oxygens, and then an OH on one side and then an OH on the other, and this is this OH that will be pointing up towards the double bond. This oxygen is slightly negative and this hydrogen is slightly positive. Notice this is now sulfuric acid, it's H2SO4. So the first step is the same as the last in the last slide. The double bond reaches out and attacks this hydrogen, and this bond will break and will add on to the oxygen. And so the first step will make a carbocation, and we've got to think about where the positive charge will be more stable, as we always have to do for electrophilic addition. You can see the right-hand carbon has two methyl groups attached to it, the left-hand carbon has a methyl group and a hydrogen attached to it, so this side will be more stable as a positive charge. The positive charge goes there, and the hydrogen will go here. The rest of it, of the sulfuric acid that's left behind, I would always draw all the bonds because it's far easier than, as it says in your textbook, which is a structural formula, if you like, of what's left behind. This oxygen will have a negative charge, and then again a lone pair needs to be drawn, and that lone pair will attack that carbon atom, and then that will attach to this to form the final product. If we then react that with water, the sulfuric acid will be made again, and an OH group will attach here instead. Finally, we're going to look at the reaction of bromine with an alkene, with electrophilic addition. So I'm going to look at the following alkene this time. It's got an ethyl group, a methyl group. I'm going to have two methyl groups on this side, just to make a point that I want to make a bit later. And then we've got bromine, so we've got Br attached to Br. Now bromine is slightly different to the others, and then it doesn't have a dipole, because the two bromines are the same element, and so there is no permanent dipole formed here. So you may ask, how does this react to this double bond? Because there's nothing for this double bond to be attracted to make the first move. The answer to that is, lies in the idea that when this Br2 approaches this double bond, the double bond will push electrons away from this top bromine towards the bottom bromine. The double bond will repel electrons in the bromine molecule to the bottom end of the molecule, and so instead of a permanent dipole, we have a temporary dipole that is induced in the bromine molecule. Now we've got a dipole, the double bond can now attack the bromine in the same way as it does before. Now we've got to think about where the carbocation will form. We've got an ethyl group and a methyl group on this side, and we've got a methyl group and a methyl group on this side. It may look like we have two R groups on both carbons, but actually Not only does the number of R groups matter, but also the size of the R group. This ethyl group will have a larger positive inductive effect than just one methyl group. And so it is this side again that has the positive charge on it because it is more stable. This side has the bromine on initially, but actually the final product will be the same either way, but you must make sure your mechanism is correct. So this lone pair will attack the positive charged carbon, and so what you'll make in the end is bromine on both sides of the double bond. And it is in fact this reaction that occurs when you react bromine water with an alkene, which is the test for an alkene. The bromine water decolorizes because the bromine attaches itself across the double bond. So now we're going to look at a couple of past paper questions. So this is our first one. We've got the reaction of chlorine with ethene is similar to that of bromine with ethene. So they may ask you to do an electrophilic addition reaction with a different halogen, but it's exactly the same as the one I've shown with bromine. It says name and outline a mechanism for the reaction of chlorine with ethene to form 1,2-dichloroethane as shown by the following equation. And there it is. So the first step says to name the mechanism, and the mechanism is electrophilic addition. You can write that anywhere in the answer space. You don't have to write it as a sentence, just write what it is. And then we're going to draw the mechanism. So first step, whenever you're doing mechanisms, is to draw out all of the bonds of the molecules. Never try and draw a mechanism without all the bonds showing. It's just a lot easier to have all the bonds there to begin with. And then you're using chlorine rather than bromine. The chlorine has a dipole. It's induced, like it is in bromine, by this double bond. And then the double bond will come out and attack the top chlorine, and the bond will break in the chlorine, and the electrons from the bond will go to the bottom chlorine. That will then make a carbocation. Now, this carbocation doesn't have a preference as to which side the positive charge should go on, because both sides have the same number of hydrogens or the same number of alkyl groups. It's the same on both sides anyway. And so this time you don't really have to worry about which side the positive charge goes, just make sure you put it on one of the sides. Then the chlorine will attach to one of the carbons, and then the leftover chloride ion, which is formed from the first step, put the lone pair in, and then that attacks the positively charged carbon, and then this product is made. This other past paper question says the alkene Z3-methylpentuene. If you're not sure what this Z means, then watch the video on EZ isomerism. Reacts with hydrogen bromide as shown below, and there's the reaction scheme. Draw the displayed formula for the minor product Q and state the type of structural isomerism shown by P and Q. So the first thing to say is that even though one of the carbocations might be more stable, that isn't to say that the other carbocation won't form sometimes. It's just that it doesn't form very often. So you get a major product which might make up 90% of your product, and a minor product formed from the lesser stable carbocation, which might make up the other 10%. So what you've got to think about here is which side will be the less stable carbocation. And they've already given you the major products, that makes things a lot easier. So for the major product, you can see the bromine has been added to this third carbon along. And so the minor product will be where the bromine is added to the second carbon along instead. So a displayed formula for Q, and remember a displayed formula shows all the bonds, so we're going to do that. 1, 2, 3, 4, 5. We've got a bromine on the second carbon, and a hydrogen on the third, and then fill in the rest, CH3 there, and the rest are hydrogens. The type of structural isomerism you'll recognise from Chem 1. You can see that the position of the bromine has changed from the third carbon to the second carbon, and so this is a position isomer. You do need to remember your Chem 1 knowledge for the Chem 2 exam. Please email me if you have any questions on electrophilic addition that you are unsure of from this video.